Well, first of all, thank you, Lou, for the long introduction. I think you've taken away half my speaking time, but that's okay. Um, so let me just get to the first slide here. First of all, before I get going on the presentation, I need to acknowledge some people. And the first ones are my graduate students, Eddie Berkey and Trevor Van Dyke, who have worked with me on this project. The project is part of a long-term project on the origin of the deposits, the metamorphosed massive sulfide deposits in Colorado. And as was alluded to by Lou, we started doing this almost 20 years ago. The thoughts and ideas that we've put together on this are not our own, and they're based on a lot of input from a variety of people. And these include the people at Zephyr Minerals, who in part financially supported the project. And this includes Lauren Comperdo, Will Felderhoff, and Mark Graves, and also some consultant geologists in Colorado. One of your DREGS members, Brian Allers, and also Stan Keith, John Shallow, and Monty Swan. It was a real pleasure sort of being out in the field with Stan and Monty talking about various issues on the outcrop. A couple of other people I need to acknowledge are Graham Teal, a consultant I've worked with in Australia on Broken Hill type deposits and many other metamorphosed massive sulfide deposits, and Adriana Hyman, who worked with Graham and I on the Garnite story. Now, while I'm going to focus on the rocks near Colorado Springs, El Plomo, Dawson, and Green Mountain, this is also part of a longer term project on some of the other deposits. And some of the samples provided for that part of the study were from Karen Kelly at the USGS and also the Denver Museum of Nature and Science. So let me tell you why I got involved in this project in Colorado. And it's two main reasons. One was because of the garnite that Lou mentioned, and he's correct. As part of this study that I did many years ago, we looked at over 100 occurrences around the world. And as Lou correctly pointed out, Broken Hill and Colorado were the two standouts in terms of the volume of garnite spatially associated with mineralization. But the second and probable main reason for getting involved in this project was related to this map that I've got up on the screen, which is dated, and it may be incorrect, but this nonetheless is why we got involved in this. And Graham Teal, my colleague, sort of pointed out to me that with this osseous reconstruction that was modified from Brookfield in 1993, that the east side of Australia sort of was supposedly up against the western side of the United States. And if you look at Broken Hill right here, it sort of forms part of a continuous of the Yavapai province in Colorado and through the central United States. So this is what got us excited. And so Graham and his boss at the time, John Lynch from Lynch Mining, came over to Colorado, and we all went and started looking at about a dozen deposits that were part of a project that Sheridan and Raymond did for the USGS back in the early 80s. And who showed us around at the time was Brian Allers, and this is how we got to meet Brian. So we started on this almost 20 years ago. So let me just tell you that the Proterozoic represents a time when some of the world's largest base metal and gold deposits were formed, and in the United States, there were Proterozoic VMS deposits in Arizona and Wisconsin, and you're all aware of the large gold deposit at Homestake at Leeds, South Dakota. There are at least 20 Proterozoic base metal and gold deposits in central Colorado. They're all generally small. As I mentioned, I'm going to focus on Dawson-El, Plomo, and Green Mountain, but they will be discussed in context with others. And I think that's an important thing. You just can't go to Dawson-El, Plomo, and Green Mountain and come up with the at least a story that I'm going to sort of put forward to you. The other thing about these deposits is they've been metamorphosed. So the ones in the western side over near Gunnison have been metamorphosed to upper greenschist, lower amphibolite facies, but that extends to middle and upper amphibolite facies around Salida and Canyon City. There have been conflicting genetic models that have been put forward for how these deposits formed. Sheridan and others, Sheridan and Raymond, basically suggested they were VMS deposits. Heinrich in the early 80s suggested they were skarn deposits, and a couple of other ideas that have been put forward, but these are unpublished. On the Zephyr Minerals webpage, you'll see that we've sort of suggested there is some affiliation to Broken Hill type deposits, and the work of Stan Keith and Monty Swan through an unpublished report to Zephyr Minerals has suggested these are shear zone hosted peroluminous granite related deposits. I will say right at the beginning that we intend to wrap up the project at the end of next year, where Eddie will be finishing his master's thesis, and we hope to present, as Lou mentioned, at the GSA under the umbrella of PC2. So what I'm going to talk to you about today is preliminary, and we've done several things that we will present at that time, but I'm going to focus on the mineralogy and the petrology today. So the aim of the overall project was to determine the origin of the base metal mineralization and evaluate the effects of metamorphism on the deposit, and to potentially use major and trace element compositions of oxides and silicates and the presence of unusual rock types as exploration guides. And I just want to show you a couple of images here, and I'll talk more about these later on. This is this nodular sillimanite rock, and you'll see that this is actually quite common, associated with several of the deposits. And this is some core from the old Plomo deposit, where you can see this sphalerite, pyrite. There's a little bit of galena and chalcopyrite in here, and you can see there's little black dots in here, and over here you can see this is some of the garnite in the quartz, and I'll get back to that as well. I don't have much time to talk about the regional geology, and I'm no expert. I'm sure more of you in the audience know a heck of a lot more about the regional geology and tectonism of central United States than I do, but let me just point this out. There have been the Dawson and property sits pretty close to the Yavapai Mazatzel boundary in this sort of transition zone, where the Yavapai province and the Mazatzel have been accreted onto the Archean Wyoming province, and the Wyoming province is Archean and aged about 2.7 billion years. See that Yavapai, the orogenic episodes about 1.78 to 1.69 GA, the Mazatzel 1.68 to 1.60. Now, one of the things I want to stress here is that the ages of granitoids that occur in Colorado ranges from about 1.73 to about 1.36 GA, and there's been nothing done on the age of the mineralization except some lead dating of galena many years ago, on not in the Dawson area, but in the Greenville area, and it yielded an age of about 1.72, which coincides with the Yavapai orogeny. The rocks are metamorphosed and they're highly deformed, and I'll just show you this image here, and I'll talk to you about a bit more about it later on. But this is just a plot based on some of the whole rock analysis of the granitoids in the Dawson area. And they suggest this particular plot of rubidium versus yttrium plus niobium suggests that these granitoids are probably volcanic arc related, which is consistent with the previous models put forward for the granitoids in Colorado. So two maps here, one on the location of the deposits, and the other is the metamorphic facies. So this is a diagram was taken from the Sheridan and Raymond paper from '84, And we visited all of these locations, including some just sort of west of Denver at Evergreen. But I've highlighted a couple of names here: Gunnison, Cinderella, Cotopaxi, and this is the Dawson-El Plomo-Green Mountain deposits. You can see that the approximate metamorphic facies are upper green schist, lower amphibolite near Gunnison, gets a bit higher over near Salida. And when you get over to Canyon City, it's getting pretty close to middle to upper amphibolite facies. And as you go down to the southern part of the wet mountains, you get up to granulite facies. So before I talk about Dawson-El Plomo-Green Mountain, let me talk about some of the other deposits first. And so what Eddie and I decided to do was to go out to Gunnison and look at the least metamorphosed copper, zinc, gold deposits. And these occur in the Du Bois greenstone metavolcanic rocks, and you can see that it occurs in a belt from west to east. There are at least 9 deposits that have been identified here. And so they largely occur in the metavolcanic rocks, but they are spatially associated with the metasedimentary rocks. And yes, there are granitoid intrusives there as well. Drobeck and Sheridan and others suggested these were VMS deposits. It was in part location of the deposits within in the volcanic rocks, the elongate strata-bound nature of the ore bodies, the laminated sulfides parallel to layering and crude banding in some of the ores. But this is probably related to deformation. But the one I also want to point out to you is the spatial association with magnetite-bearing quartzites and supposedly a meta-chert. I'm going to talk about very briefly here the largest massive sulfide deposit in the district, and this is the Vulcan zinc, copper, gold, silver deposit. The size and the grade is unknown. The massive sulfide lenses are spatially associated with quartz sericite and quartz chlorite to a lesser extent. The massive sulfides consist largely of pyrite, chalcopyrite, and sphalerite, so copper and zinc. But here's something I also want to stress to you is the late overprint of other elements, mercury, bismuth, and copper. And for those that didn't know this is the type locality of 3 copper tellurides: vulcanite, ricardite, and weissite. As I mentioned, Drobeck and Sheridan and others suggested these were VMS deposits. But the question we asked was, are these the less metamorphosed analog to those further east over near Salida and Canyon City? So here's Vulcan sitting right in the middle of these metafelsic or meta-basic volcanics with metasediments around the outside. And here are the syntectonic granitoids and diorites. Here are a couple of images of the Vulcan deposit. I imagine several of you have been here. This is the ugly looking spoils pile from the Vulcan deposit. Here is this particular view is of this outcrop right here. Whoops, sorry. I'll get to it in a moment. Is this particular outcrop here. And this is on its edge. It's deformed, stretched out, largely muscovite and quartz here. This is what the sulfides look like. Pretty massive pyrite with some pyrrhotite. And this darker sample over here has a lot of sphalerite in it as well. So pretty massive looking ore here. All right. So go from Gunnison over to Cinderella Bonton and then to Cotopaxi before I talk about the deposits near Canyon City. So here's a map that's been put together by John Shello, Brian Allers on the Cinderella and Bonton mines. And despite the color differences here, these are largely metasediments. The greenish pale green color is the sillimanite gneisses. And you can see these sort of symbols in here, the little pods. This is the nodular sillimanite rock. And here we have an image of the nodular sillimanite rock as well. The mineralization is spatially associated with gedrite, anthophyllite, cordierite, garnite rock. And some of the nodules actually have garnite sitting in the cores of them. So we think that the nodular sillimanite rock is a strata-bound zone of alteration where the more mobile elements have migrated out, leaving the less mobile elements such as alumina. But the presence of garnite in the cores of these things suggested that zinc has been part of the hydrothermal fluid that may have passed through these rocks. Also want to point out this sample here of rhodonite that occurs right in the alteration zone. And I'll get back to rhodonite a little bit later on. There is some gabbro in the area, but it's largely just metasediments. Okay, over to Cotopaxi this time. Here's a map also put together by, this is put together by Salotti many years ago. And once again, you can see that the dominant rock type here are metasediments. The mineralization is located over here. There is a spatial association to an amphibolite. The yellow patches here are this nodular sillimanite rock. Again, here's some of the nodular sillimanite rock we see in outcrop. The mineralization, once again, is spatially associated with a garnite, gedrite, cordierite rock. And these two other samples, this is massive sphalerite, and this one is chalcopyrite from the ore zone. These two samples are actually from the collection of the Denver Museum of Nature and Science. Nodular sillimanite rock, as I mentioned, it's pretty common. And here are a couple of samples from Cinderella, but it's also associated with the Independence deposit, which is just north of Salida. This whole, the bottom of this cliff here is the Independence deposit. And this whole wall is of nodular sillimanite rock. Have a look at the size of some of these nodules. This particular piece here is about 1 foot in length. And yes, I have a very old cell phone here for scale. All right, over to the Dawson area. So this is a map modified from Taylor and others back in 1975. And if you have a look at this area around Dawson, okay, there's Mesozoic material to the north, but it's largely in basement gneisses and granitoids. And this is supposedly the Dawson shear zone that goes from Dawson through El Plomo down to Green Mountain. And so this appears on Zephyr's webpage. And this is the Dawson section, which is mainly copper and gold. The El Plomo section is zinc, lead, and silver. And Green Mountain is copper, zinc, silver, and gold. So there is some elemental transition over this approximately 12-kilometer distance here. This is an image taken from the Keith and Swan Zephyr report. Canyon Spring, Colorado, Canyon City is behind us at this stage, and you can see the Dawson segment from town. This is the Dawson segment, Windy Gulch segment, Windy Point segment, and this is a view from Windy Gulch looking back at Dawson. And the mineralization sort of, whoops. I'll get this right in a moment. Sorry, guys. Right, here I am. So the mineralization occurs sort of across this zone in here. So this also appears in the Keith and Swan report. Here's a map view. Here's a cross section. And the thing I want to point out to you is the dominance of granitoids in the Dawson-El Plomo area. We have an alkali granite between Dawson and the El Plomo section, we have a biotite, supposed biotite quartz monzonite here. And then we have a pink periluminous granite on the northern side. And you can see this occurs over here. But the important thing to note is this sort of thin brown unit, which is the metasediments, and the mineralization occurs in the metasediments. The cross-section through here shows a massive sulfide zone. The quartz monzonite would be in the hanging wall. The pink periluminous granite would be in the footwall. So we have the massive sulfide zone here. And then just below it, we have a gold zone. In places, it's about 10 to 20 feet away from the down section from the massive sulfide zone. But in places, it does touch the massive sulfide zone. Also want to bring your attention to the late stage overprint, this gold bismuth, selenium, silver, tellurium, mercury. Does that sound familiar? It's pretty close to what we see in the Vulcan deposit. Also want to point out before I forget that several of these minor elements also occur in elevated concentrations in the Green Mountain deposit as well. So just to show you the granitoids here, this is the pink periluminous granite. Here's the supposed, I say supposed because I'll show you some of the compositions of this biotite quartz monzonite. This is a soda granite, Luca granite, and an alkali granite. We have some older rocks here, a biotite rich enclave within the pink periluminous granite. We did some whole rock analysis, and yes, most of these fit in the granite field as expected on a plot of sodium plus potassium versus silica. But one of the things I want to point out to you is the biotite quartz monzonite is not in fact a quartz monzonite, but the limited number of compositions that we have put it right on the monzodiorite or in the diorite field rather than the quartz monzonite field. So in the footwall of the mineralization, the granitoids are probably 1.7 GA, and the biotite quartz monzonite is about 1.4. But I want to stress that no age dating has been done on the granitoids in the vicinity of the mineralization. So we don't exactly know the age of these granitoids. I showed you this diagram earlier on. This is just a plot of rubidium versus terbium plus tantalum and rubidium versus yttrium and niobium, showing you that these granitoids largely plot in the volcanic arc field. We've done rare earth elements as well, and the pink periluminous granitoids in the biotite quartz monzonite, which are the most abundant of the granitoids, have similar plots, except the biotite quartz monzonite has more elevated concentrations of rare earth. Both of them, as expected for granites, have negative europium anomalies, but they're pretty similar in composition, for at least from a trace element standpoint. Okay, showing you the granitoids, but there are definitely some other lithologies that are important to the discussion here. And this is this folded biotite gneiss, just to show you the fold hinge here. You can see this pegmatite sort of wrapping around that fold hinge. Here's the banded biotite gneiss. The rocks are strongly deformed, and yes, they have been sheared. So the mineralization has been sheared after it formed. Here's a conjugate set of shears here with this sort of Rydell aspect to it, cross-cutting here. So the shear zones go on this side and this cross-cutting features here. So the alteration zone that contains the sulfides is exposed in the road cuts, and this occurs within biotite gneiss. But I want to point out these two images down the bottom. This is garnite, cordierite, gedrite alteration zone. Sound familiar? Because this is what we find in the Cotopaxi, Cinderella, and Bonton deposits. There is a rather wide tremolite bearing alteration zone as well. Just some thin section images of some of the rocks spatially associated with mineralization, garnet and biotite. There's a quartz cordierite rock here. This is what the gedrite looks like. For those of you unfamiliar with gedrite, it's essentially just the aluminous version of anthophyllite. The sillimanite and plagioclase here. This is what garnite looks like in thin sections. It's spatially associated with the gedrite. And here's some outcrop with some rather coarse looking garnite associated with it. Here's a slab of core that has a quartz, pyrite, and these dark, they almost look black here, but they're dark green is the garnite. And there are patches of chalcopyrite in here as well. I mentioned the amphiboles. We've analyzed amphiboles from several of these deposits, Ace High, Amethyst, and these unnamed deposits occur in the southern end of the, or further to the east of Canyon City. And, but most of the amphiboles here, the orthorhombic amphiboles, are anthophyllite and gedrite. There's a little bit of ferrogedrite as well. The calcium amphiboles, there is tremolite, as I pointed out to you, but it's largely hornblende that it is. So there's a variety of amphiboles, and I mentioned that we hadn't completed this study. Eddie's been sort of doing some trace element work on the amphiboles, and we hope to see what this tells us about the origin of the deposit and its potential as an exploration guide. But you'll hear more about that in about a year's time, I guess. Biotite is magnesium rich, and is probably biotite for either of two, magnesium rich for either of two reasons. One, because of the alteration is very magnesium rich, which we've seen from the amphiboles, but it also could be due to sulfidation effects where the sulfur reacts with the magnesium, with the iron component of biotite, causing it to be more magnesium rich. But most of the biotite is actually on the phlogopite end of things. All right, so let's take you over to El Plomo now. This is some slabs that you see from core, garnite. This is pyrrhotite with chalcopyrite and quartz, massive sphalerite here with garnite in it and pyrite. Here's some brecciated ore, just to point out how deformed the ore is. You can see there's a rolled fragment here, almost the classic Dirtsch-Beweget that's been reported in some of the European deposits, sort of brecciated chalcopyrite zone. I'll put this picture here just to mention one thing. On the Zephyr webpage, you'll see a aeromagnetic survey, and part of the reason for the high magnetic signature is due to magnetite in some of the granitoids, and or these black spots here is magnetite. This is from an outcrop as you walk along Grape Creek near the Horseshoe Mine within the El Plomo section. Along the El Plomo section, the best ore is from the Horseshoe Mine, and there's a lot of ore still sitting on the dumps, and this is massive pyrite, pyrrhotite, and sphalerite. Some of the alteration along here, once again, is this cordierite, biotite, garnite rock. There's a couple of other images of rocks from El Plomo, sphalerite here with quartz and garnite all the way through this. And this was an image I've shown you before in the cover slide. Okay, so there is gold in the Dawson property, and this is probably going to produce the box if the ore deposit is mined. This is what the epithermal overprint looks like. This is an image that Stan Keith and Monty Swan had in their report. Look at some of the grades in here, close to 59 ppm gold in this. This is from an outcrop in one of the road cuts, about 8 grams here of gold, and in a cross-cutting vein about 70 grams. When you look at it in reflected light, in addition to native gold, there is bismuthinite, the bismuth sulfide, and tetradomite, the bismuth tellurium sulfur mineral. So as I mentioned, an overprint that looks very similar to what we see at the Vulcan mine over near the over near Gunnison. Okay, so let me talk to you about Green Mountain. So Green Mountain was the deposit that got most interest when Graham and I visited back 20 years ago. Here are a couple of images of the spoils and some of the old work, old shed and part of the processing. So why Dawson? Sorry, why Green Mountain? I know you can't see much from this map, but let me just run through it really quickly. The gray, once again, is biotite schists. The yellow is quaternary. The darker brown is the quartz monzonite. The pink is the pink aluminous granite. But I want to stress here that this nodular sillimanite rock curves all the way down through here, and this is where the old mine shaft was right here. There is a spatial association to amphibolites as well. And this is one of the most interesting samples. This is a gabbro from the Green Mountain area, and you can see chalcopyrite and sphalerite within it. Now, whether this is a replacement of the gabbro or whether this is primary chalcopyrite and sphalerite within here, I think the temperature is probably suggesting that it's replacement, but nonetheless, a beautiful looking rock. Garnite and thopholite, once again, associated with mineralization. And I'm going to talk about these two rocks in a moment. This garnet plagioclase biotite gneiss, and this garnet amphibolite, which is basically associated with mineralization as well. Okay, so when Graham Teal and I visited 20 years ago, we looked at it, we looked at each other and said, man, this reminds us so much of Broken Hill. I'll show you some of what I'm going to do is I'm going to put some images of the rock types we see at Broken Hill and some of the rock types we see at Green Mountain. For a start, we have sillimanite garnet biotite gneiss, which is the dominant lithology hosting the Broken Hill deposit. This is some of the sillimanite biotite garnet gneiss at Dawson. We see the same sort of rock at Green Mountain. So this particular rock is of great importance at Broken Hill and is one of the most studied rocks. And this is known as Proterozoic gneiss. And what it is a quartz biotite sillimanite rock. And you can see the little white things here. This is plagioclase, and we have garnets as in the cores of these things. A lot of geochemical work has been done on it, and it's been proposed that this is a metamorphosed rhyolite. And the reason this is particularly important in Broken Hill is it occurs underneath the mineralization, and it's most closely associated with minor Broken Hill type occurrences in the district. So we see this same rock type at Green Mountain. We also see it at Dawson. So as I mentioned, there's great difficulty in trying to work out the precursors of the rocks in the district due to the deformation and the pretty high grade of metamorphism. And so these are potentially some volcanic rocks spatially associated with mineralization. Here's the garnet amphibolite at Green Mountain. At Broken Hill, we're at higher grades, and this is essentially equivalent to the rock we see at Green Mountain. We have a 2-pyroxene granulite, orthopyroxene, clinopyroxene, and these spots in here are garnets, and the whole things have been flattened due to deformation. We see this rock. Here's a nodular sillimanite rock at Green Mountain. We also get nodular sillimanite rocks at the Pinnacles deposit right next to the large Broken Hill type deposit. Just to point out to you, and I have an image later on if I get time to show you this, the nodular sillimanite rock next to the giant Swartberg or Black Mountain deposit in the Akenese district of South Africa, pointing out that we see this nodular sillimanite rock next to a variety of VMS metamorphosedex deposits worldwide. We have iron formations associated with mineralization. in the Dawson Green Mountain area. This is banded iron formation at Broken Hill. It's a little different from what we see at Dawson. This is a magnetite spessartine garnet apatite rock, but there is also quartz magnetite rock at the second largest deposit in the Broken Hill district, the Pinnacles. So there's this quartz here and magnetite. Here is banded and massive iron formation from El Plomo. We also see banded iron formation at Dawson. So a lot of rock types similar to what we see at Broken Hill. Here is another one that really caught my eye. The major rock type that is spatially associated with the Broken Hill deposit, the altered rock, is a quartz garnet rock. It's been called a codicule in the past, or a quartz garnetite. We get the exact same rock at Green Mountain. Garnets here, quartz. Some locations a bit more biotite, but we also get biotite garnet quartz rocks at Broken Hill. And we think at Broken Hill, these are metamorphosed exhalative rocks or zones of metamorphosed alteration. Okay, garnite. Garnite is intimately associated with mineralization at Broken Hill. You can see the green garnite here. Here's a massive sphalerite here. But there is a blue quartz garnite rock, all these little dark spots here are zinc spinels. And as I've emphasized repeatedly here, lots of garnite associated with the ore in the El Plomo, Dawson, and Green Mountain deposits. So if you look at the Zephyr webpage, one of the things I put together was a comparison chart about similarities between the Broken Hill deposit and the Dawson-El Plomo Green Mountain mineralization, particularly Green Mountain. One of the things is similarity of age, 1.72 if you believe the age, the lead age from the galena. Broken Hill is 1.69 plus or minus 3, which would actually overlap that age. Upper amphibolite versus upper amphibolite granulite facies, deposits of both roof-related sequences, and the rock types that I've just mentioned before are all listed down here. There's strong zinc, lead, copper zoning in the Dawson-El Plomo Green Mountain trend, and there is also strong zoning from footwall to hanging wall in the Broken Hill deposit. People don't talk much about the copper aspect of Broken Hill, but the footwall feeder zone is enriched in copper. And at Broken Hill, it has really high lead to zinc ratios, whereas at Dawson, it's a lot less lead, but high silver to lead. I'm going to talk about hogbermite in a moment, but there is magnetic pyrrhotite, or the monoclinic variety of pyrrhotite associated with mineralization at both Broken Hill and Dawson. So I'm just pointing out the similarities. I'm not necessarily saying that Dawson-El Plomo Green Mountain is a Broken Hill type deposit, because there are several differences as well. The dominant sequence in a Broken Hill is metasediments and metavolcanic rocks. Below the deposit, there are granitoids, but there are also mafic sills below this in a package of metasediments. They're really high-grade lead, zinc, silver deposits. The Broken Hill deposit runs about 20% combined lead and zinc, which is pretty extraordinary, and silver concentrations of averaging about 150 grams per ton. And when you realize this is a 200 to 300 million ton ore deposit, this makes it the largest single massive sulfide occurrence in the world. In contrast, most of the deposits in Colorado are copper zinc deposits. There are some that contain a little bit of lead, but most don't. And these deposits in Colorado are more enriched in gold relative to silver. One of the things that's characteristic of the Broken Hill deposit and Broken Hill deposits in type deposits in general is they're dominated, the gangue mineralization is dominated by pyroxenoids, bustamite, wollastonite, and rhodonite. And I showed you that picture of the rhodonite from Cinderella for a reason. It's one of the few locations where we've seen a pyroxenoid. So let me take you back for a little bit to the garnite story. And this is a summary of a diagram that I put together back in 86. And what it is a ternary plot of the zinc, magnesium, iron components of garnite. Zinc here, magnesium here, iron over here. And what we did was we took all the data, over 2,000 data points from worldwide locations, and put it on this diagram. Cut a long story short, pegmatites sort of sit along this boundary down here. They can be zinc rich down to about halfway along the zinc iron end continuum here. Garnite found in sillimanite gneiss sort of plot more to the hercynite end. This is the hercynite. This is Spinel sensu stricto, and garnite, pure garnite would be up here. Aluminous-rich granulites sort of fit along the magnesium and iron join. In some marbles, they're magnesium-rich, but probably 95% of the world's garnite, especially associated with metamorphosed massive sulfide deposits, has this compositional range right here. Very characteristic. Why does it fit into this range? Is because the garnite invariably coexists with sphalerite and pyrrhotite. And what this does is buffers the sulfur fugacity, which in turn controls the zinc to iron ratio in the spinels. And we show this from experiments done in the lab. So when you look at the garnite compositions from Colorado, a lot of them do plot in this particular field, but there's a heck of a lot, and they're quite different from any other location anywhere in the world. A lot of them plot in this field over here, or as we put it, metamorphosed massive sulfides of magnesium, calcium, aluminum rich rocks. So why do they occur over here and not in this area? Well, what happens is you can write a reaction that involves sphalerite and garnite, zinc sulfide going to zinc spinel. You can write a reaction of pyrite or pyrrhotite iron sulfides going to hercynite, but you can't write a reaction of a magnesium sulfide going to magnesium spinel. There is no magnesium sulfide. So what happens is you form compositions over here, but if the bulk rock composition is magnesium rich, it essentially just drags it towards this particular corner over here. When we take the garnite compositions from Dawson-El Plomo-Green mountain, it overlaps this boundary between the two. Those that are found in iron aluminum rich rocks form in the expected field you see worldwide. And when there is a lot of gedrite, the magnesium amphibole, you start getting towards the magnesium member. If you're wondering what garnite looks like in hand specimen, it's this beautiful green crystals form octahedrons. This is what it looks like in thin section. And sometimes a little bit of hematite exudes out of it later on, and you can get this rather dark looking, ugly looking mineral in thin section. I mentioned the mineral hogbamite. Hogbamite, as it happens when I've been doing studies of metamorphosed massive sulfide deposits, this rather rare mineral hogbamite pops up. What is hogbamite? It's essentially an iron, magnesium, zinc, hydrated spinel. This should have a bracket over here, but it has titanium in it as well. And we've looked at these from various locations around the world, and basically on a plot of zinc plus manganese, on the other corner, magnesium and an iron, those associated with massive sulfide deposits has rather characteristic compositions. We found it at Dawson. This is what it looks like in thin section. It's the brown mineral here, and we've sort of circled it here. But we've also found it at the Independence mine, and also in the Evergreen hydrothermal zone just west of Denver, where you see a beautiful cordierite garnet anthophyllite rock, spatially associated with minor copper mineralization. We had a paper published on this location several years ago. Okay, so let me try to get to the end of the talk and just give you a preliminary discussion on some of the models that have been put forward. Heinrich suggested that these deposits were skarns. And this is in large part because of the spatial association and the dominance of granitoids in the central part of Colorado. But there's no direct relationship of the mineralization to carbonates in the copper zinc deposits. There is a spatial association of granitoids to the copper tungsten skarns. And the copper tungsten skarns in Colorado occur in clusters, but they don't overlap spatially with the lead zinc mineralization. The other thing I want to put forward to you is I don't know of too many copper zinc skarns worldwide. You can get copper skarns, you get lead zinc skarns, iron skarns, tin tungsten skarns, but copper zinc skarns are pretty unusual. And the gangue mineralogy that we see is atypical of skarn mineralization. It's also hard to explain how you get iron formations, quartz garnet rocks, and zones of stratobound hydrothermal alteration that you don't normally see in skarn deposits. The pyriluminous granite and ore deposit model, generally when you see pyriluminous granites and you have mineralization associated with it, it's with lithium, tin, tungsten, rare earth elements, and not generally with zinc, copper, lead deposits. I don't know of zinc, copper, pyriluminous granite related deposits worldwide. There is a spatial association of the mineralization to metasediments and possibly to metavolcanics. And it's hard to explain the presence of the sulfide garnite amphibole horizons. These are not products of igneous differentiation of granites. Okay, the VMS model. I've got this diagram that was put together. I forgot the author's name now, but basically what we have is VMS occurrence on the seafloor. But I want to point out this particular horizon. These are strata-bound footwall zones of alteration. So the hydrothermal fluids come up, and if there is a rock type that is easily replaced, you'll get these strata-bound zones of alteration. And this is possibly what is reflected by the nodular sillimanite rocks and the garnite-bearing rocks. They do form horizons here. The metallogeny signature is characteristic of VMS deposits. In the Gunnison area, there is definitely a spatial relationship between volcanic rocks and the mineralization. As I mentioned, these strata-bound zones of alteration. Faults may have served as hydrothermal feeder zones. And the metamorphosed alteration mineral assemblages that we see are characteristics of several metamorphosed ore deposits found worldwide. In particular, the Montauban deposit in Quebec, it has a lot of similarities to what we see here. They have nodular sillimanite rocks, the garnite rocks, and as it turns out, they're roughly the same metamorphic grade. The cons against this is that there is a dominance of granitoids rather than volcanic rocks, and the volcanic rocks at present are damn hard to identify. I mentioned the Potosi equivalent is possibly a metamorphosed rhyolites. There are mafic igneous rocks, there are some gabbros. And as I mentioned, the camouflaging effects of metamorphism and deformation makes it pretty hard to go back and see if there's a volcanic or volcaniclastic component to the metasediments. And I've talked about broken hill type mineralization. I've talked about a lot of the similarities, but here are some of the cons against the broken hill type model. And that is the sequence that Broken Hill is dominated by metasediments and volcanics, metavolcanics rather than granitoids. BHC deposits are really massive high-grade lead zinc silver deposits. Those in Colorado are copper zinc deposits and essentially lead-free. And we don't have the characteristic gangue assemblage that we see at Broken Hill, even though we have a bit of rhodonite at Cinderella. So why am I showing you this diagram? So this year I put together a paper with Graham Till on Broken Hill type deposits. So now what our story was for this was to evaluate all the deposits that have been described as Broken Hill type deposits worldwide to actually see whether they are indeed Broken Hill type deposits. And all these deposits listed in yellow have sort of fallen under that umbrella in various publications. And what our conclusion was that most of these deposits weren't in fact Broken Hill type deposits, but they're either clastic, metamorphosed clastic SEDEX deposits or metamorphosed VMS deposits, or some of the Swedish Bergslagen type deposits. But we did recognize that there were some deposits that looked like they were transitions either between BHT type deposits and VMS deposits. or BHT and carbonate hosted SEDEX deposits. So this is, at this stage, this is what we're suggesting. Most of the deposits look like VMS deposits, but some have broken hill type affinities. So let me just finish off the presentation by these summary points. The Dawson-El Plomo-Green Mountain trend occurs in the transition zone of the Yavapai-Mazatlan provinces, which is the assemblage of accreted oceanic terrains. The peroluminous granitoids in the Dawson area dominated by an earlier pink banded granite, later monzonite, whose age we don't know, but we're assuming based on ages of similar rocks in central Colorado, their ages. They show trace element compositions of a volcanic arc source. I had a diagram that showed that most of the granitoids have a rhyolitic composition, they're extrusive equivalents, but the only definite rocks that would suggest, well, the definite rocks that we say are metamorphosed volcanics are the, excuse me, metamorphosed rhyolites we see at Green Mountain and Dawson. We see iron formations, garnite-rich rocks, nodular sillimanite rocks, potosi rocks, and garnet amphibolite rocks at Green Mountain, and some of these in some of the other locations. As I mentioned here, we think they're probably VMS deposits, but they definitely have some BHT type deposits. So we're suggesting there's probably a hybrid model here. And some of the deposits, Vulcan, Dawson, Green Mountain, have this later epithermal overprint, which is probably Miocene in age. The nodular sillimanite rocks, the presence of garnite and hogramite can serve as exploration guides. And there's plenty of garnite and nodular sillimanite rocks in Colorado that are worth tracking down in the search for these types of deposits. And I think I will end it there. Thank you for your patience, and sorry if I spoke fast in my Australian accent.
Thank you, Paul. That was an excellent presentation.